So thank you very much for joining today. Nice to see you here and welcome to this monthly touch base on virtual thermal sensing technology by Newtwin. Nice to meet you all. I'm Giuseppe Nicolis Gro and I will be your host today. I'm the head of growth for Newtwin and I brought with me Milo, the Soricellis, that is also working at Newtwin as a chief technology officer. The idea of this session that we are hosting every month is to bring together people from the industry, practitioners, to share some updates and best practices around thermal management for high power density components, especially within the automotive sector. So without further ado, let's start this session. There are more people joining. So let's start this session. As you can see from the screen, it's a monthly recurrent one, and we're gonna see what's happening in the virtual thermal sensing space. So as Newtwin, we have the pleasure of working with many practitioners, companies, researchers, and academia players around the world on topics of efficiency, performance, and safety of high power density components across different industries. Our main focus nowadays is the automotive industry. And the topics that we're going to discuss today is a few software topics around the virtual thermal sensing. So what we can say about this technology, how this technology is complementing or replacing some industry standards, like, for example, thermal networks or AI/ML approaches, or some different approaches as well. So without further ado, the starting point of the discussion is the global market situation around the power density and the increased power density of many systems around the electrification. So we are seeing this happening around mobility, industrial, space tech, marine, and so on and so forth. And the increasing demand for power density and within the electrification systems is basically highlighting how the current sensing technologies cannot really keep up with the pace of the increased power density. Today, we're going to focus our discussion on thermal sensing, so on how basically the thermal aspect is managed. And the reason why we are doing so is because the biggest bottleneck in this kind of systems is for sure the thermal aspect. So the understanding and managing the complexity of the thermal dynamics across those kind of systems and components is what exactly is required to manage the expectation in terms of efficiency, safety, and cost. So it's probably the biggest bottleneck around there. Not only is very important, but is also across what we are seeing around the globe is also the biggest. It has the biggest blind spot in the industry. So there are a lot of solutions to replace or complement existing sensors, but in terms of thermal sensors, the situation is it's a bit more complex than that. So the starting question is, how is temperature calculated in real time for de-rating strategies? So when those kind of components, we can think about, the automotive components such as ePowertrains, e-axles, electric motors, DC-DC converters, inverters, and so on and so forth. How is the temperature monitored and measured in real time at critical points to inform the de-rating strategies? What we are observing around both Newtwin customers but also industry standards is something like this that you can see on the screen. So many best practices are starting from some physical measurement, so some kind of, for example, NTCs mounted on board on the system, and then since it's impossible to really mount the NTCs for several reasons, most of the critical points, so for example, on the junction temperatures or on the junction of the semiconductors or on the rotor of the eMachines, there is some kind of correlation between the physical measurement of the NTCs and that, let's call it, most critical point. Since this correlation is very difficult to obtain, we're going to discuss why in a second, and companies knows that, and then it's quite well renowned in the academia. The point is that the NTCs and then the correlation is not enough because it's not really accurate and reliable across all operating conditions. And this is the reason why all the companies that are working industrially with this and are bringing this kind of system into production, they are adding a safety margin on top of that estimate. This safety margin is going to be the core of our discussion today. Because having the best designed system, so very high performing system, whether it's an electric machine, 2-in-1, 3-in-1, on the design phase, but then not being able to take the maximum out of those kind of system because of safety concerns, a maximum in terms of, for example, performance, and having to rely on those safety margin, it's really bringing down and reducing all the value and the effort done in the pre-development and development phases. So how to reduce this catalytic safety margin is going to be the core of what we're going to discuss today. We are going to start with a couple of examples. So here you can see what I was discussing before. So this is a power module. On the left of the image, you can see where usually an NTC is can be placed, so where the sensor can be placed. And we have taken an example in which the measurement of the NTC can be, for example, around 70 degrees Celsius. And on the right, you can see where actually you like the sensor to be placed. So on the junction of the semiconductor. And where the sensor measures 70 degrees, for example, we kind of think from experimental data, customers, and so on and so forth, that under certain condition can be around 200 degrees. And this is exactly the correlation that we were talking before. So we can have a correlation that states something like when the NTC is measuring 70 degrees, my junction temperature is around 200 Celsius degrees. But I cannot really put a physical sensor there. And that's the first limitation in terms of placement of those kind of physical sensors. The second limitation is around the breadth of information. So on the left, you can see again a red dot where, for example, you could think about measuring the temperature on an electric machine, but on the right, you see the distribution of the temperature. So the information that you want to control those kind of systems and extract the maximum potential in terms of efficiency, in terms of performance, in terms of safety, having a small or a reduced information only in one or in few points is not enough, especially if you want to control complex systems like, for example, electric machines or oil-cooled electric machines. So there are many solutions that are raising to cope with this problem. I'm sure that many of you that are today here are already adopting these inside your company, whether they are, for example, thermal networks or other solutions. The problem is that we are not seeing many of those solutions arriving in production with success because they are not really a valid replacement for physical sensors yet, at least. So if we're talking about many solutions, the four dimension in which we are evaluating those are the accuracy. Are those solutions accurate in estimating the temperature dynamics? How much accurate with respect to, for example, test bench experiments? And are those measurement or estimations reliable? So the software estimation, is it reliable across all operating conditions or just on a subset of extreme cases that I have tested in my test bench? Are those software solutions scalable? So can I replicate easily that software solution across different systems without having to build something that is heavily relying on that specific system and measurement and structure? And the last but not least, is the software solution compliant with the regulation, especially for the automotive sector? So the answer to these questions today are mostly no for all the solutions that we are seeing within the academia and within the industrial landscape. The two main solutions that we are seeing are thermal networks and artificial intelligence and machine learning models. However, both these approaches are not really giving a positive answer to those questions. And we could talk about this for hours probably. We could have an entire session. If you are curious about this, happy to organize a dedicated session with some of you. But the point is, I'm going to summarize the three main challenges here. So whatever technology you can use, whether it's, for example, thermal network or artificial intelligence machine learning based models, they have three main blockers. First, both systems have a very big trade-off in terms of how accurate is that model and how big is that. So how much you can run it real time on the edge. So if you want a thermal network that is very accurate, that is monitoring more than 1 point, and it's doing it in real time, then you're going to obtain something that, it's not that small, that can run in your embedded system. The second one is about the calibration. So both thermal networks and artificial intelligence machine learning models, they require a lot of data to be trained. So you really want to calibrate those models across all the whole spectrum of operating condition. This is very difficult to do, and is also very costly. And the last but not least of the main blockers of the current technology landscape is that they are very system specific. So whether you're building a thermal network or you're building a pure AI machine learning model, they're very system specific. It means that if you build for one specific system, then you need to basically start from scratch for another one. And input-output interface across the whole product development cycle, from the simulation team to the control team to the final firmware, is gonna be painful in many cases to replicate and scale across the whole let's call it system that you are developing, whether it's a 2-in-1 or 3-in-1 or similar. So since those are the limitations, what we are seeing around the market is that those solutions are not really implemented. So software solution to complement and or replace entirely physical sensors are not really being implemented at scale. And this, again, is hindering all the efforts that engineering teams are doing throughout the product development cycle. It's hindering the design efforts, the performance, the safety, and the cost. And it's hindering that because since the estimations of temperature and the correlation in between those physical sensors and the place in which you would like to measure to do to inform the derating strategies, they are not that accurate. The industry is adopting very high safety margins. We're talking about 20, 30, 40%, even 50% in the worst cases that we have seen across, for example, complex cooled electric machines. And this is not only hindering the performance and safety, but also the cost, because basically you are over-engineering your product line. So the technology that we are working on at Newtwin, but not only at Newtwin, we are seeing developing at the market, it's called virtual thermal sensing. And the concept here is having a software solution that has all the benefit of software solution, of being a software solution. So no sensing placement limitation. That means that you can have, you can have it estimating temperature at all points in which it's impossible to do with a physical sensor, but also the reliability of a physical sensor. So the reliability in terms of accuracy, and also across not only the accuracy on a specific subset of operating condition, but a stable accuracy across the entire spectrum of operating condition. So the technology that we are going to discuss today is a software technology that is able not only to complement physical sensor, but to replace them entirely. And that's exactly what we would like to discuss today. The idea is having this virtual thermal sensor technology and reduce the safety margin while at the same time increasing the safety of the system. While increasing, because what we're observing is that despite engineers and engineering teams are over engineering the components and leaving those high safety margins, what we are observing is that those safety margins are very big on average, but there are some small subset of cases in which they are not tested, in which actually those safety margins are not big enough, and there is a serious risk threat in terms of security and safety for the system. So why are we discussing this technology? Those are the reasons why you should have a look at this kind of technology, also beyond what we are discussing today. So virtual thermal sensing technology is very accurate. We are talking about, on average, plus minus 3 Celsius degrees. If not, with many customers that we are seeing that are implementing this technology, we are also well below the threshold. So we're talking about plus minus 1 Celsius degrees. It's not only accurate, because many of the solutions that you are implementing for sure need to be accurate. For example, if you're talking about thermal networks, they're not only accurate, they are reliable. It means that accuracy is not only the accuracy in the worst cases that you can measure on a test bench, but is the accuracy that you obtain across all operating conditions and range of the system at different different coolant flow rate, a different coolant temperature with different external temperature, a different torque speed if we're talking about electric machine, and so on and so forth. So the accuracy is important, but you want to measure your software solution also in terms of reliability. And if you want to bring this into production teams, you also want this to be scalable. So you want a software solution that is accurate, is reliable, but can be replicated with similar input-output interfaces across every system that you're building. And this is, I would say, another very important information to bear in mind when we are talking about physical sensing replacement, software physical sensing replacement. The last point is about compliance. We are observing that many purely artificial intelligence or machine learning models are, black box based, and it's not very easy to make them compliant with the automotive regulation, especially for, divergence problem. There are many problems there. Is not going to be the focus of today's session. Again, if you're interested, please do reach out to me, to Milo, or to the rest of New Twin team, and happy to discuss it more. Happy also to get your, experience in this domain. So this technology that is accurate, is reliable, is scalable, and is compliant has many use cases. So it's exactly the same technology. We have, as New Twin, we have developed this methodology, we have refined it. There are many pieces around, and Milo is going to discuss it in a second. And we have developed also a tool to work with this. But the point is, the same virtual thermal sensing methodology is applicable without many changes to all the system and subsystems of the ePowertrain, and virtually, hypothetically, across all electromechanical systems. But our customers, there are some, public references that you can see, in which you can also dive deeper into those cases, and you can also have a look at our next events. We're going to bring many of those customers and new customers to explain, what they have done with this technology. They've been applied, the virtual thermal sensor technology, on eMachines, traction inverters, onboard chargers, and many more system and subsystem, with the precise goal of having an accurate and reliable estimate of the temperature in real time where it really matters. So if we're talking about, for example, the eMachines having those kind of estimates on the head windings, on the rotor magnets, on the bearing shaft. If we're talking about the inverters, about the surface, the junction temperature of the power modules, the coolant flow rate, for example, the coolant temperature, the bus bar, and many other. And if we're talking about the onboard chargers, again, it's a very similar case to the inverter. But that's mainly what we are going to discuss today. And I try to give you some context into why this technology is being deployed across automotive markets, and why you should care about this, and really assess whether virtual thermal sensing can be a viable solution to improve the efficiency and the cost and the safety of the system that you're building. How to do it? We're going to see it now. So for this, I'm going to leave the floor to Milo, that is working across many different customer cases and can explain you a summary on how this is done technically. So from start to end, what this virtual thermal sensing methodology entails, what are the upside, the downside, and what you should take a specific eye on when talking about this. So please, Milo, the floor is yours. I'm going to leave you share the the deck with the technical information about this.
Yeah. Thank you, Giuseppe, for the introduction, and hello, everybody. Let me share the screen. Second. And presentation mode. All right. So let's start by giving you an idea on what are the steps required to successfully build a virtual thermal sensor. And here in this slide, you can already see the final workflow, basically, which is mainly composed by 4 steps, plus, of course, the code generation. So compared to other fully data-driven approaches taken by our colleagues out there, so maybe purely black box, as also Giuseppe have said a couple of words about them. We do not discard classical physics-based numerical approaches that typically are employed by engineering across all the industries, and therefore our starting line is a full order model derived from an available CAD CAD drawing combined with the well-known finite element analysis. But of course, as you all know, a full order model would be completely impractical to use in real-time embedded application. And therefore, model order reduction comes into play as a second measure step that need to be taken in order to simplify, so to produce a simplified version of the full order model, which is basically an essential step for reducing the complexity, the numerical full order model, while holding the same accuracy. And then there is the third step, which is actually the most important, the crucial one, which is actually the calibration. So as we all know, a full order model, so a model which represents physics, has always some inherent simplification, because the real world is very complex to model. Therefore, we always take some step of simplification when we build a full order model. And therefore, a digital model is typically not accurate when compared to test bench and field experiments. So we might have a range of plus minus 20% of accuracy on our target variables. And that's why having the possibility to calibrate our digital model becomes very crucial in order to obtain a model that can be reliable and can be used in a real-time embedded hardware for making estimation over time. The fourth step, actually, it is what we call discrepancy modeling. So let's make a step back. So as you may know, AI has gained momentum over the last few years. And in particular, its application in the context of scientific modeling, it's trending, actually. It can be used independently or alternatively to physics-based approaches. But more interestingly, the data-driven algorithms can be combined in a complementary fashion, making the whole simulation architecture very effective in real-world application, where particularly challenging nonlinear phenomena can affect the output of a system. If we think about an electric motor, which may be oil spray, cooled by oil spray, for example. So we have multiple physics domains that are acting on the same system, and they are impacting the thermal evolution of the system itself. So by modeling everything with a pure physics-based approach, this would become infeasible to obtain a model that can run in real time. And therefore, what we call discrepancy modeling, it's a very effective way to take all the unmodeled effects and then guarantee a reliable estimation of the target temperatures of the system. And then finally, the last step is the preparation of the code for the deployment into the embedded hardware, by optimizing, of course, the hardware resources utilizations and the real-time computation of and update of the model at each iteration. So as we have said, the starting point is the finite element model constructed upon the mechanical CAD, which is typically always available during the design process of a component. By nature, the finite element numerical approach provides a fidelity description of the underlying thermal physics with a high resolution, which can be actually controlled by the grade of the mesh, how fine is the mesh. And therefore, a fine 3D mesh can be seen as a fully connected and very detailed thermal network, which describes the heat diffusion on the system topology. And as you can imagine, this kind of model encode intrinsically already a lot of information about the physics and the thermal evolution of the system. So it is very important to use it as a starting line. And then we have the model order reduction. We can spend a couple of words on it and saying that, of course, in literature, there are multiple techniques available, such as balance truncation, moment matching, and of course, they are not simple techniques that simply remove node of the original full order model, the original mesh. In fact, the model order reduction reduces computational complexity without modifying the mesh. Let's say, in fact, basically, you can think about that model order reduction finds a low-dimensional representation of the thermal system, identifying the fundamental characteristics. So you end up describing the same exact initial problem provided by the finite element approach, but with a very small set of linear equations. And of course, the model order reduction procedure provides also the so-called projection matrix, so which is actually a nice feature because it allows to reconstruct with a very high accuracy the temperature in any area of the original full order model. And then we end up having a very small digital model which holds the same accuracy of the original one and let us inspect variable of interest, in this case temperature, in any point that we desire. And then we step into the calibration phase, right? As we said before, this is very important. And simulated systems inherently deviate from real physical systems due to the complex effects, which might not be modeled. And therefore, as a result, unlocking the possibility to calibrate the model is fundamental. Calibrating the model is equivalent to solve the inverse problem if you think about it. So we have parameters, we have a target experimental measurement that we might have recorded on the test bench or acquired directly in the field during the operation of a prototype component, and would like to calibrate the model so that it matches exactly the evolution, the temperature evolution of the target measurement. In this scenario, the availability of a reduced order model plays a very important role. In fact, it would require a huge amount of time to execute thousands of transient simulations to find the best parameter to describe the physics based on the full order model, because the full order model can be very, very big in terms of numerical parameters. And thanks to the reduced order model obtained in the previous step, we can do it very effectively and obtain a final calibrated digital model which is suitable for real-time estimation. And the discrepancy modeling. So as I have briefly told before, applying machine learning in this context, it ends up being very effective. In fact, on one side, you can think about we can leverage the machine learning to uncover complex nonlinear patterns in the data, which may be very expensive to encode into the physics-based model part. And on the other side, we can exploit domain knowledge provided by the physics-based model counterpart to avoid overfitting during the training of the artificial neural network, and also to contain the size and the complexity of this network, which is beneficial for the microcontroller memory usage. Of course, we need to say, though, that in this context, naive implementation of classical artificial neural network architecture does not work well. In fact, discrepancy models must retain certain properties, certain characteristics, which are a key for a successful application in real-time safety-critical software architecture. And this peculiar neural network, for example, have several benefits. So one of these, which is very important, is the stability. They need to guarantee that the output of the estimation cannot drift over time. It's always stable and safe and reliable. They are also lightweight, so they are very small network, and also they require a low amount of data, which is typically important because this would increase a lot of the effort of preparing this kind of discrepancy models. And as intangible it can be, a virtual thermal sensor here in this slide is actually presented a visualization of the final architecture. So a virtual thermal sensor is indeed a cluster of software components that work together. And as you can see here, basically fundamental architecture is composed as follows. So we have a loss model. So the mathematical model which explain how the losses and the heat is generated inside the system. We also have a cooling model which is actually the counterpart, so how the heat is extracted by the system. And then these two blocks are fed into the thermal model, the physics thermal model, which is constructed from the full order model to the reduced order model through the calibration. And then finally, this is complemented, as it has been said before, complemented by discrepancy model, which is absolutely optional. In certain application, it is not need to leverage data-driven model. In other applications which are more challenging from the uncertainty of the application, then we can complement it. And as you can see, the discrepancy model will work in parallel and will act and correct the estimation, which is then provided to the output of the firmware solution. And then finally, here a more practical slide in which we can actually explore a bit more the implementation of these the virtual thermal sensor in a couple of use cases. So once we have prepared the architecture, then it can be deployed inside the firmware solution. So we can say that we have information available in real time that cannot be measured, so they were not available before. The first natural thing that we can do is actually to use this information to integrate inside the control loop of the system. And here I present a couple of cases which are relevant for the automotive field and for the thermal management. On the left side, we have a power converter case, simulation of a power converter. And on the right side, we have an electric motor. Let's start from the power converter. So in the, let's imagine, for example, that we have a three-phase traction inverter. The most relevant variable that we would like to measure or better estimate in real time is actually the junction temperature of our power modules. Junction temperature, it is very critical, of course, because it is related to the aging and to the failure of the component over time. And of course, having a virtual thermal sensor that can estimate the junction temperature accurately, then I can not only reduce the safety margin that I have for the power derating, but I can also leverage an interesting concept, which is here addressed as TLO, which is the time limited overrating. So typically data sheet, according to the data sheet that is provided by the supplier, the manufacturer of this power module, that there is a time limit defined that ensures that the possibility of safely exceeding the maximum temperature without causing a hard fault in the component, although aging still occurs. Having an accurate real-time estimation of the junction temperature is extremely useful in this case, because based on the TLO, the supplier and the manufacturer in his facility in the laboratory provides mathematical model for the aging, which are prepared during endurance test of various prototype. And of course, this one requisite in order to use this aging model is to have at disposal in real time the junction temperature. So actually, having a VTS in a power converter not only helps us to maximize the performance during the fast transient operation of the system, but as you can see here, we can act on two variables. We can act on the switching frequency, modulating it, and also on the amplitude of the current, always trying to control the junction temperature directly to its limit. Not only that, because then we can also leverage aging function in order to monitor the state of function of the traction inverter over time. On the right-hand side, instead, we have the electric motor case, where we propose a couple of scenarios. On top, we have basically the monitoring of the stator winding temperature. So what is important in electric motor are mainly two things. One is the insulation of the winding, and the other one is the rotor magnet temperature. Of course, these two temperature can also have a very different thermal scale, thermal constant time. In fact, the winding heats up very fast and cool down also very fast, and instead the rotor has a completely different dynamic. So having the possibility to place a virtual thermal sensor on the winding insulation allows us also to maximize the peak torque, because I can directly derate the current that is injected applied to the electrical machine based on the temperature of my VTS on the winding. Instead, for the rotor magnet, we typically in production, there is no way to directly measure the temperature of the rotor. Therefore, it is quite crucial to have some sort of model, because, for example, if you imagine a driving cycle, so during an on-off cycle, that since the rotor thermal constant is very slow, the rotor temperature has not enough time to cool down, and then it eats up over time, and then very quickly we can reach a situation in which the rotor is close to the critical temperature. Therefore, having let's say that in terms of control, if we cannot predict the forward temperature of the magnets using a reliable virtual temperature sensor, achieving a stable derating to maintain safe temperature levels for both the stator winding and the rotor magnet would be impossible. And this highlights the fundamental importance of virtual temperature sensor in maximizing both the peak torque duration and the continuous power output achievable by the machine. Okay, so we arrived till the end, and I hope I gave you a good overview on the steps required for building effective virtual thermal sensors. Of course, many of you might recognize the complexity of the process and the multiple skills required, which traverse different engineering domains such as finite element methods, numerical simulations, optimization, algorithm, data processing, machine learning, and embedded control systems. We at NewTwin have recognized this problem early, and we have packed the entire workflow into a single software platform, which allows the user to progress and complete all these steps that I have described without having deep expertise in any of the various subjects. And if this is aroused your interest, of course, we will be happy to show you the software in a practical implementation demo.
Thank you, Milo, for explaining everything. And I think there is also one question already. So while maybe you can, if you want, Milo, you can have a look and answer. I think partially we already answered, but please take the question. In the meantime, I encourage everyone in this session, if you have any question, any doubt, any comment, please write it in the Q&A tab at the top of Teams, so we can take the questions and try to answer at best as we can. The question is, does your software solution also do FEA modeling and aero and ROM creation, or is something you take from traditional FEA software? Milo, please.
Yes.
You were already answering this.
Yeah, exactly. Thank you for the question. Of course, our software basically, so the step I've described are actually all of them, starting from the full order modeling included into the software platform that we have developed. Therefore, you can definitely prepare the full order model and the physical model into the platform, and not only it, you can also generate and prepare the reduced order model inside the platform. Of course, we are not limited to delegate everything to our software, but if you already have some pieces of your model already prepared in other software, which is the typical case that happens in industry, because maybe during your pre-development design of the system or the device, you are using also other finite element analysis software. We also support the possibility to import directly a full order model by holding for example, the finite element model, so the mesh that you have, without changing it, and using it for preparing the reduced order model. So we are quite flexible and open to it. Yeah.
Thank you for the question, and thank you, Milo, for the answer. Any additional point or topic? In case you have not now, but you will, start thinking about these and have question, please do reach out to us. Follow our events. We have one monthly session to give the industry update on these topics, on what we learn, what we see around. We are also going to share the slides and the recording of this session, so you can have it. It's been a pleasure to host you all. So thank you very much for joining today, and we wish you all a great day, night, or evening, or afternoon, as I'm seeing people from different countries. So thank you very much. Have a great time ahead.